Okay, we should get started. This is very loud. It's really nice to have Ben come here. He comes to us from UNH, where he just finished his class at 1 o'clock, which is why our schedule this week is a little delayed to give him time to get here. So Ben did his undergraduate work at Yale and his graduate work at Princeton, and he's now at UNH, and we're all very anxious to hear about Parker Solar Probe. One of our Dartmouth undergraduates helped build it. She went to Berkeley and was a technician building pieces of the innards of it, and so I'm happy to hear about it. And I think I'll just let you go. Okay?
Thanks very much.
Yeah.
Is this on enough? Yeah. Yes, please. Thank you. It's a pleasure to be here and to tell you about the Parker Solar Probe and also the solar wind, one of the objects that the Parker Solar Probe will be investigating. Before I begin, I just want to mention that I'll be presenting some new work. This is more of a review talk than a new research talk, but there will be some new results presented. And the new results I'm presenting will involve a number of collaborators whom I've listed here. I won't go through all of them, but you'll see some of these names appear again later in the talk. So I'll begin by telling you a little bit about this new NASA mission, the Parker Solar Probe, which is going to explore closer to the sun than we've ever been before. I'll tell you a little bit about the spacecraft, but then I want to tell you mostly about sort of ideas behind the origin of the solar wind, which is one of the science puzzles that the Parker Solar Probe is going to help us to solve. So I'll give you some background on the solar wind and then talk about what is arguably the leading theory at the current time for how the solar wind is generated. And that's via the action of waves that are generated by the sun that propagate out, become turbulent, dissipate, and end up accelerating the wind away from the sun. And finally, at the very end of the talk, I'll come back to the Parker Solar Probe and just to discuss more broadly some questions that will be resolved by the probe. And I'll try to keep this under the hour so that there's some time for questions at the end. And if there aren't questions, this can also be expanded considerably if needed. So this is an image taken the morning of August 12th of 2018. This is a long-term exposure of the launch of the Parker Solar Probe. It might look like it was a failed launch, but that's actually not the case. It is recently flown by Venus, and it is now about half an AU from the sun. So the standard unit of distance in the solar system is the astronomical unit, or AU. We sit at 1 AU on average, and the Parker Solar Probe will ultimately get to about 0.05 AU. The closest any spacecraft has been before is 0.38. So this is going, in some sense, 6 times closer to the sun than we've ever been before. This is a picture of the spacecraft before it was launched earlier this year when it was at NASA Goddard being tested for flight readiness. You can see this is actually the part of the spacecraft that will face the sun. It's the heat shield. And because it's going so close to the sun, a big issue for the spacecraft is protecting the instrumentation, primarily against the intense sunlight. The black body temperature at 0.05 AU is, I actually don't know the exact number, but it's over 1,000 Kelvin. And so many ordinary materials would melt that close to the sun. What I mean by that is if you put a black body at that distance from the sun, it was absorbing energy and re-radiating energy would heat up to a very high temperature. And so this heat shield here, which is, I believe, mostly silicon carbide, is designed to withstand and survive in that environment. The vast majority of the instrumentation will be lurking in the shadow behind the heat shield. And there are a number of instruments back there. There's an instrument to measure magnetic fields at what we would consider low frequencies, so frequencies, say, under a hertz in fluctuations in the magnetic field. There's a search coil magnetometer to measure high frequency variations in the magnetic field. There are electric field antennae that will come out, actually, they will be in the sunlight. They'll come out from the sides of the heat shield. It will tell us the electric field at the spacecraft's location. There are also particle instruments which will measure different particle species. So the majority of the particles in the solar wind, where the Parker Solar Probe will be sitting, are protons and electrons. They comprise most of the flow as they comprise most of the baryonic matter in the universe. There will also be an instrument here that will measure alpha particles as well, which are, after protons and electrons, the next most abundant ion species. There are also some other instruments that will measure the very small minority of particles that are accelerated to really high energies, particles that will be accelerated at shocks, for example, up to energies of MeV or more. So a bunch of instruments that will be kind of lurking in the shadows, and one brave instrument, in addition to the electric field antennae, that will be sticking out from the side of the heat shield. This is a Faraday cup, which will be the only instrument that will actually receive the bulk of the solar wind and the bulk of the sunlight as well, incidentally, all the time. And it will tell us a lot about fluctuations in the density, temperature, flow speed in the solar wind, which we'll use to analyze this medium. A lot of this I've already said. This is a picture here of that spacecraft orientation. So it's always going to be reorienting itself when it's close to the sun so that it faces the sun with the heat shield forward. Farther away from the sun, it will actually rotate because it has solar panels and it will want to expose those to sunlight for power. But that will be during parts of the orbit when it is farther from the sun. Shown here are a bunch of, well, it's the trajectory of the spacecraft within, the part of this, the trajectory within 30 solar radii from the sun. So to translate to AU, 1 AU is about 215 solar radii. The closest that the Parker Solar Probe will get to the sun is just under 10 solar radii. And the closest we've been is 60 solar radii. So all of this part of the orbit where the probe will be measuring a region we've never visited before. And this is a very interesting region for trying to understand the origin of the solar wind. I've said this word a number of times without really defining it. I realize I'm defining it a little bit later, but let me just mention what this is for those of you who haven't heard the term before. Basically, the solar wind is a quasi-steady, quasi-radial outflow of material from the sun. It's coming out all the time in all directions. And it's basically hot plasma, hot ionized gas that reaches, gas that's so hot that it becomes ionized. And it reaches supersonic speeds, highly supersonic speeds by the time the flow reaches the Earth. And the origin of that flow is still a mystery to scientists. And this region that this probe will be visiting is a region where this flow is still being strongly heated and accelerated, but we haven't been able to visit it before. So those measurements that I was mentioning before of electric fields, magnetic fields, flow velocity, temperatures, particle distribution functions in phase space, also energetic particles, in this region will really revolutionize our understanding of the solar wind and its origin, as well as some other physics as well. Physics of shock acceleration of particles, for example, things that I won't actually address in this talk. Let me amplify a little bit about the solar wind and present some broader background on what it is. So here's the artistic rendering of the solar wind and how we might conceive of it. This wind coming off the sun. Here's the Earth sheltered by its magnetic field and magnetosphere. The solar wind emanates in all directions from the sun. Part of it comes and hits Earth's magnetosphere, leading to very interesting interactions there that give rise to space weather and disturbances that can affect manned space flight, satellites, even terrestrial power grids on the ground. Some numbers for the properties of this plasma outflow. At a heliocentric distance r, distance from the center of the sun, of 1 AU, that's the distance of the Earth to the sun, typical flow speed in the solar wind ranges from 300 to 800 kilometers a second. So Mach numbers of 20 or more, typically, for this plasma. The temperatures on the order of 100,000 Kelvin. Densities are very low, several particles per cubic centimeter. It can be tens of particles per cubic centimeter in some types of solar wind. The total mass carried away from the sun by the solar wind, the amount of mass per year, the mass loss rate, is about 10 to the minus 14 solar masses per year. The age of the universe is on the order of 10 to the 10 years. So at the present rate of mass loss, over the lifetime of the universe, the solar wind isn't a big part of the mass budget of the sun. It's not changing the mass of the sun appreciably. Also, the luminosity, the mechanical luminosity associated with the solar wind, which is really the kinetic energy radiated in the solar wind, is about 1 part in a million of the electromagnetic energy radiated by the solar wind. And so the solar wind isn't a really big part of either the energy budget or the mass budget of the sun. Nevertheless, it's still very interesting to space physicists for a number of reasons. One is it is a theater in which all space physics occurs, be it propagation of shocks from the sun out to the planets, or propagation of energetic particles, interactions between outflows from the sun and the Earth's magnetosphere, giving rise to space weather. Another reason that is of interest to the scientific community is that it's an extraordinary laboratory for studying plasma physics. There are things that we can study in the solar wind that we cannot reproduce in a experimental setup on Earth. For example, high Reynolds number turbulence. Turbulence in which you have a driving of fluctuations at very large scales, orders of magnitude larger than the scales at which the fluctuations dissipate. You can measure that in the solar wind. A phenomenon like magnetic reconnection, something which I imagine some of the plasma physicists colloquia have addressed in this department, and actually which I know you'll hear about next Tuesday when my colleague Roy Torberg visits, I believe, to give a colloquium here. He'll mention that too. Reconnection is something else that we can measure in the solar wind as well. And so it's very interesting to plasma physicists. And lastly, I'll say one final thing is that it is in some ways a model for understanding other astrophysical outflows. So we can measure with satellites like this Parker Solar Probe, but many other satellites that have been launched historically, all kinds of properties of this outflow, and try to understand how compact astrophysical objects can generate outflows. And if we can understand that well in this system, we may be able to understand better how these outflows work in more distant astrophysical systems. So there are two types of solar wind, fast wind and slow wind. And the relative role in relation of the two is illustrated in this plot. This plot is illustrating data from the Ulysses spacecraft, which flew out to, basically, it was launched from Earth, went out to Jupiter, did a flyby, was launched into an orbit that was highly inclined relative to the ecliptic plane, the plane of the Earth's orbit around the sun. And then it swept over the sun and completed actually 3 orbits. And this is, I believe, from the first orbit. I could have that mistaken. But what you're seeing here is a polar plot of solar wind outflow velocity. Here's the ecliptic plane, horizontally the sun at the center. The distance from the origin to this curve represents the speed of the solar wind at that, basically, latitude. So when the Helios spacecraft was over the poles of the sun, the speed was 700 to 800 kilometers a second. That, or below the south pole of the sun. That speed is characteristic of what we call the fast solar wind. Down here, the ecliptic plane, the speed drops to about 300 kilometers a second or so. That would be the slow solar wind. This is how the solar wind looks throughout most of the solar cycle. But during and near the phase of the solar cycle where you have most sunspots, the so-called solar maximum, this picture becomes much more complicated. You alternate between fast and slow wind at basically all latitudes. But for most of the solar cycle and in most of the volume, the fast solar wind is the basic state of the flow, and that's the part of the wind that I'm going to be focusing on in this talk. And the origin of this wind has been puzzling to scientists for a number of years. And the reason can be understood by considering some of the early studies of the origin of the solar wind. These date back to the seminal work by Parker 60 years ago, the same Parker for whom this spacecraft is named. And he predicted the solar wind even before it was measured. There's a great story about this seminal paper, which is famous to those of us in the field, but not famous to necessarily everyone in the scientific community. But when he wrote this paper, he submitted it to the Astrophysical Journal, and he got, I believe, 3 referee reports. They all rejected this paper. This crazy idea that the sun is emitting this supersonic outflow all the time. And it was only through the intervention of the editor, who was Chandran, that it was actually published. And then later on, it was measured and verified. And he became a professor at the University of Chicago, had a great career. In fact, this was just one of an extraordinary number of things that Parker has contributed. The Sweet Parker reconnection model, for example. Many things he's done, but this was one of his triumphs. But with in his early model of the solar wind, and actually the models of several other people who worked on the solar wind origin problem early on, what they did is they basically modeled the solar wind as a spherical outflow, hydrodynamic outflow, that was energized basically by thermal conduction. So it was taken as an assumption that the coronal base was fixed at some temperature that was constrained by observation. So say 1 million Kelvin, 2 million Kelvin. And then heat can be conducted away from that boundary. And then you just have conservation of mass, conservation of energy, you have a momentum equation for the evolution of the wind far from the sun. It was assumed that the flow was spherically symmetric, radiation was ignored in these studies. The problem that all these studies came up against is they couldn't explain these fast solar wind speeds. They would typically get 200 to 300 kilometers a second for the outflow speed at 1 AU, not 700 to 800 kilometers a second, which is the basic state of the flow. They also offered no explanation for why the corona itself is so hot at 1,000,000 Kelvin. The photosphere of the sun is only 5,800 Kelvin. So it's puzzling why the corona could be over 2 orders of magnitude hotter than the surface of the sun that we see in visible light. So the conclusion that many came to after these early studies is that the dominant energy flux in the solar wind cannot be that thermal conduction heat flux. It has to be something else, some non-thermal heat flux. And one of the leading ideas, the first proponent of which I believe was also Parker in this 1965 paper, although at that time not with many details, was that the energy flux is carried by some kind of plasma wave, in particular the Alfvén-wave. Let me talk about that a little bit more. I will describe these Alfvén waves in a bit more detail in a moment. In fact, I'm going to skip ahead and come back to this slide. I'm going to grab this slide here. Let me describe what an Alfvén wave is for a minute. So to understand these plasmas over global scales, large scales, comparable to the size of the sun, a good approximate model to understand the plasma is a fluid model, which neglects the fine scale structure of the plasma in phase space. It just focuses on bulk properties of the plasma, like density, flow velocity, say current, the magnetic field. And the fluid model that I have in mind is called magnetohydrodynamics. This is a version, ideal, adiabatic MHD. Ideal meaning that these equations here have no dissipation, there's no viscosity, no resistivity. Adiabatic because I put in an equation here that basically expresses the idea that if you follow a fluid element, its specific entropy does not change. It makes an adiabatic flow. But these other equations here describe basically perfectly magnetized plasma at large scale. Scales much larger, for example, than the gyro radius of a charged particle gyrating in a magnetic field. This is an appropriate model for large scales in the solar, for some phenomena. So let me talk about these equations. The first equation is basically mass conservation. It's the continuity equation. Imagine integrating this over some volume in your plasma that's a fixed volume. The first term, rho, is the mass density. So you integrate over volume, you get the mass in that volume. And so that's the time rate of change of that mass. Rho times the velocity v is the mass flux. You apply Gauss's theorem, integrate this over that fixed volume. The divergence becomes the surface. The integral of the divergence becomes the surface integral. The surface integral of the mass flux, dot dA. Well, that's just the rate at which mass is flowing out of your volume. This is stating that mass is neither created nor destroyed. The second equation here, B is the magnetic field, P is the thermal pressure. This is basically Newton's law. So you see a dv dt that looks like an acceleration, but in the fluid, the acceleration you care about is not a partial time derivative of a flow velocity. You care about the change in the velocity of a moving partial of fluid. And that time derivative is given by a partial of t plus v dot grad of the velocity. This is basically acceleration of a fluid element times mass density. So this is mass density times A. This should be force density. And it is. You have a gradient of pressure pushing you from high pressure to low pressure, and then you have these magnetic terms. There are two types of pressure, magnetic forces rather. One is a pressure force, a magnetic pressure force. That's the force arising from this term. It affects a fluid in exactly the same way that pressure does. B squared over 8 pi mathematically acts the same way as P. It pushes material from high magnetic field regions towards low magnetic field regions. This term, B dot grad B, is a magnetic tension force. It arises if you take magnetic field lines and you bend them, they want to bend back and straighten. All right, so that's F equals ma. What about this last equation lurking down here? This is basically Ohm's law for a perfectly conducting plasma. It's a statement that the electric field in the moving plasma frame vanishes. And so if you then transform to the lab frame, the electric field becomes in our frame E plus V cross B. Rather, let me reverse that. The electric field in the moving plasma frame is E plus V cross B over C in Gaussian CGS units. Take the curl of that and apply Faraday's law, basically this equation here. The significance of this equation is encapsulated by the second statement here. It implies this law, the so-called frozen-in law. That equation tells you that the magnetic field lines can be thought of as threads that are frozen to the plasma. So as the plasma moves, these field lines move with the plasma. All right, so if you put together this idea of the frozen-in law with this magnetic tension force, you immediately arrive at what an Alfvén wave is. So basically, you have a magnetic field in a plasma, magnetic field line in a plasma, and you bend it, it wants to bend back. If you disturb the plasma to the side, the field line will bend. You'll get a magnetic tension force that will pull you back. And you can have waves on a string where the magnetic field line is playing the role of the string. And that is the Alfvén wave. And the group velocity of this wave is the Alfvén speed, which I've written here. The group velocity VA grows as the field strength grows, it decreases as the density grows. Which makes sense in a way. Let me go back now to how these Alfvén waves play out in the context of the solar wind. So there are really three stages of how this works in the solar wind. The first is the sun launches these waves. The outer third of the sun by radius is convectively unstable, so it's constantly churning in a turbulent fashion. And the foot points of magnetic field lines that are anchored in the photosphere are constantly shaken by this convective motion. And that shaking launches these Alfvén waves, waves on a string. They go away from the sun, they become turbulent. Their energy cascades from large scales to small scales. That's something I'll talk about more in a moment. And then at small enough scale, small enough wavelengths of the waves dissipate, heat the plasma. That heating increases the thermal pressure plus wave pressure that accelerate the wind away from the sun. So how about this first stage? Is there any evidence for this launching of the Alfvén waves? There is. This is a movie taken from this is a movie constructed from data taken from the Hinode Solar Optical Telescope by Bart de Pontiu and colleagues. What you're seeing is the limb of the sun. This is the low corona. This down at the bottom here, I believe that is I think that's a photosphere or it could be the top of the chromosphere, I'm not sure which. What you're seeing here are filamentary structures. These are structures in which the electron density is higher because the light you're seeing is basically Thomson scattered sunlight. So brighter regions have more electrons in them. The electron structures, these filamentary structures, are elongated along the magnetic field lines because charged particles can move very freely along magnetic field lines, but not across field lines. They undergo these tight helical spirals, so they can't move across the magnetic field. But you can see that these structures are waving back and forth. And that wave motion, waving back and forth, is this Alfvén wave motion that I was talking about. These authors tracked features in this movie, or in this data, to measure the delta V, the fluctuating velocity of these waves in the low corona, and determine the energy flux carried by these waves, which is basically energy density, which is rho delta V squared, rho is mass density, times the speed at which the waves are carrying that energy away from the sun, which is the Alfvén speed. They obtained this estimate, which is basically what you need to power the fast solar wind. Yes, Christine.
Could you just say what the time scale of that
I
movie
was just
is?
going to ask that.
These are like 5, 10, 20 minutes would be the time scales of these.
From frame to frame, or for the...
No. For the, if you think about the characteristic wave motion there, that would, if you were to try to, you can't really see complete periods of the motion, but they estimate that the wave periods are on the order of 10 minutes, something like that.
Is that kicking at the top? Is that hours or minutes?
If I had to guess, that would be, it's funny, I've shown this movie about 10 times and I never noticed that. I would bet those are minutes and hours and minutes.
Okay.
I know in the, hours are 0, and then the it's minutes and seconds.
Yeah, so it's minutes. It's like a 45-minute long movie.
Yeah. So this basically is sort of evidence that this is a plausible scenario energetically. Okay, maybe there's enough energy being released from the sun to power the wind, but how would it actually work? It's not enough to just release energy at the base and say, look, this is the wind. Something needs to play out farther from the sun. So let's talk about that. That's really what I wanted to focus on in this talk, was this process of how the waves become turbulent and energy cascades. What do I mean by energy cascade or turbulence? Well, the example that we usually draw upon to understand turbulence is hydroturbulence, hydrodynamic turbulence. You can think of turbulence in water, for example, is a process in which you stir a big eddy, a large eddy, that then breaks up into smaller eddies, which then break up into smaller eddies still. And you can think of this process No, well, eventually the eddies will dissipate at small enough scales because viscosity will prevent really tiny eddies from turning over. And abstractly, you can think of this process as you're putting energy into a system when you stir that energy, that eddy initially. You're putting energy in at large scales because you created a large eddy. The energy cascades to smaller scales. That's the process of eddies breaking up into smaller eddies. And then the energy is dissipated at small scales, converted into heat. And so we talk about the cascade of energy being that process of eddy breakup. Well, another idea for hydrodynamic turbulence that's going to play a role in my discussion of Alfvén-wave turbulence is illustrated here, is the idea for the eddy turnover time and the turbulent heating rate. The time it takes for these eddies to break up is of the order of their size divided by the fluctuating velocity across the eddy, the delta V. The time for the biggest eddy to break up is its size divided by the total RMS velocity of the turbulence, because although these smaller eddies have their own fluctuating velocities, those are smaller than the fluctuating velocity of the biggest eddy. If you ask how much time does it take to take the energy of the initial eddy and get it all the way to the bottom of the cascade and dissipate it, it turns out that time is taken up mostly by the turnover of the largest eddy. Because the smaller eddies, although they're slower, they're also smaller and they turn over faster. So you turn over the large eddy once, the rest of the stuff takes maybe another 50% of time total, no matter how far down you go in size, because it gets faster and faster the turnover rate. So the heating rate is energy density divided by the time it takes the largest eddy to turn over, and that's your heat rate, rho delta V cubed over L. All right, how about Alfvén waves? Well, we even bring up the idea of turbulence in the context of Alfvén waves. The reason is that the Alfvén wave in the plasma is basically undamped. So in the absence of turbulence, what would happen? We launch that energy from the sun, and it basically is going to propagate out to Earth without damping. It may push the plasma a little bit on the way, but it won't get you a solar wind. The thing that turbulence does is it accelerates the dissipation of that wave energy. In fact, as I will argue, it can convert that wave energy into thermal energy quite close to the sun. Not all of it, but basically you get roughly, say 20-30% of the energy out every time you double the radius. Something of that order is what we're finding in these models. Let me try to explain some of that some more. Again, using the framework that I mentioned earlier of ideal adiabatic MHD. I'm going to now get into a slightly more technical part of the talk, but please stop me at any time if you have questions. So it turns out you can learn a lot about these Alfvén waves by just rewriting those MHD equations, as I've shown here. So here are some new variables. All right, the total velocity is a background flow capital U and a fluctuation delta V, magnetic field V naught plus delta V. For Alfvén waves, the fluctuating velocity delta V is perpendicular to the background field, as is the fluctuation of the magnetic field. Also, the velocity fluctuations are divergence-free. We then form the so-called Alsacer variables, delta V minus plus delta V over square root of 4 pi rho, it's C plus or minus. The Alfvén velocity is V naught vector over the square root of 4 pi rho. Total pressure is thermal pressure plus magnetic pressure. If you make this set of substitutions in the MHD equations, and in addition, you set capital U equal to 0, and you assume the background is all homogeneous, you get this equation here. I've left some blank spaces here, and I will fill those in a moment. You can immediately, from looking at this form of the equation, figure out a couple of important things. The first thing is that these Z plus or minus fluctuations represent the Alfvén waves. They are Alfvén wave amplitudes. They are quantities that are simply advected at velocity plus or minus VA, as you can see from the form of the left-hand side of this equation. So if you ignore the right-hand side, go to the linear limit where you can ignore these quadratic terms. Z plus or minus, the solution for it will be any waveform that moves at velocity plus or minus VA along the background magnetic field. The second thing that you can see is, well, the Z plus and Z minus represent waves propagating in opposite directions. Z plus along the field, Z minus anti-parallel to the field. The other thing you can see is the form of this nonlinear term here is very interesting. There's a Z minus, there's one Z minus and one Z plus in that term. Z minus plus dot grad Z plus minus. That means if you have only waves moving in one direction, they don't lead to any nonlinear term. And it's a nonlinear term that's giving you turbulence, because if it was a linear equation, the sum of 2 solutions would be a solution. The sum of 100 solutions would be a solution. You launch 100 waves, they're just going to propagate through each other, because their sum is still a solution of the equation. To get waves to interact, to get energy to cascade, you need a nonlinear term. And in order for that to happen in this system, you need counter-propagating waves. This is a problem for the sun, because the sun, by causality, can only launch outward propagating waves. So we immediately have the first big problem, which is how do you get the inward propagating waves to interact with those outward propagating waves? Well, here enter these other terms that I didn't write down before. These are the terms that arise when U is non-zero and you allow the background to be inhomogeneous. In particular, I allow the background here to vary with distance from the sun. I'm not taking into account strong gradients in background quantities perpendicular to the background magnetic field. This is actually a set of equations that has been studied for a long time, even before some of these studies. Well, there's another 1980 paper by Hyman and Olbert, which really pioneered much of this approach. And these terms, they couple z plus and z minus and they're linear terms. They actually give rise to wave reflection. And actually this relates to the question about the time scale of those waves in that movie. Those time scales are large enough that the radial wavelength of these waves is, in some cases, bigger than a solar radius. And so this is not the WKB limit of short wavelength, high frequency waves that just propagate without reflection. The Alfvén speed itself is different between the front and the back of one wavelength. That leads to partial reflection of these waves. And that, if going back to this nonlinear term, is how we're going to get a coupling between counter-propagating waves. So much as the outward waves, they partially reflect, the outward waves interact with their reflection. All right, so now I am going to discuss in detail how this happens. And this is perhaps a little bit ambitious, but I think it's important enough. It's like one of the key ideas that the solar probe is going to test, and it underlines our understanding of the solar wind. So I think it's, maybe if there's like one point that you take away from the talk, it's the punchline of the next like 12 slides. So I'm going to give it a try. There'll be some math. So I want to understand how this reflection-driven turbulence works. The waves go away from the sun, they partially reflect, and they cascade. Can we describe that mathematically in some interesting way? Let's do it in 2 steps. We're going to first understand the so-called WKB evolution of Alfvén waves in the solar wind when they don't reflect, and then we're going to add in the turbulence and the energy cascade. See how that modifies the WKB evolution. So the WKB evolution, so the evolution of waves with short wavelengths, high frequencies. A nice way to start to understand that evolution is actually the simple pendulum. So imagine the following scenario. You have a mass m on a string of length L that's threaded through a hole in the ceiling. Gravity is down. If L is constant, the frequency of small amplitude oscillations is the square root of G over L. The energy of the pendulum is the sum of kinetic and magnetic energy. Conserved. What happens if we start slowly pulling the string to the left? Is there still a conserved quantity? For example, is the energy still conserved? Turns out no, it is not, but there is a conserved quantity. It's the action. In fact, energy divided by frequency. If you pull the string slowly, in the sense that this number, epsilon, dl dt absolute value divided by omega L, if that's much less than 1, the time rate of change of J, well, as epsilon goes to 0, the time rate of change of J goes to 0 faster than any power of epsilon. This is called an adiabatic invariant, the action of the pendulum. It turns out there's an analogous result for waves in the WKB limit in an inhomogeneous medium. You can think of this collection of Alfvén waves as a whole bunch of pendulum in the solar wind, a whole bunch of oscillators. And there's also a conserved action. And the way you write down the conservation law is in this form. If you recall the equation of mass conservation, the continuity equation from the MHD equations, they have the same kind of form. A partial time derivative plus a divergence is 0. That's a conservation law. Here, the quantity in parentheses is the action density. Omega prime is the wave frequency in the local plasma frame. Omega is the frequency in the lab frame, say an inertial frame centered on the sun. E omega is wave energy per unit volume per unit omega, at frequency omega, and C is the wave group velocity. In this case, that would be the Alfvén speed relative to the local plasma. Let's take that equation, multiply it by omega, and let's assume that the background flow is time independent. If the background flow is time independent, omega is going to be a constant for any wave. Omega doesn't change as the wave moves away from the sun. That means that omega can come inside those derivatives. That means that what we really care about is the ratio of omega to omega prime inside those derivatives. Well, let's take the background flow U to be parallel to the background magnetic field, and let's take them both to be radial. So here, I'm not trying to introduce a magnetic monopole, I'm thinking of a split monopole. So the radial field lies outward in the northern hemisphere, inward in the southern hemisphere, something like this, to the sun. Then in that case, omega prime, frequency of the wave in the plasma frame, this is the Alfvén-wave dispersion relation. Omega prime is Kr times Va. In the sun's frame, we have to consider the Doppler shifted frequency. Omega is just Kr times U plus Va. U plus Va is the rate at which the waves are moving away from the sun. Va is the rate at which they're moving with respect to the plasma. And C, this group velocity of the waves, is R hat times the sun, U plus Va. So omega over omega prime in that equation, I can replace it with U plus Va over Va, as I've shown in the bottom equation. I'm just copying that equation over. Let's integrate this over omega. What's interesting is that the only thing inside these derivatives that depend on omega is E omega itself. So you can integrate over omega to replace wave energy density per unit frequency with a total wave energy density, which is just rho z plus squared over 4, where this is like a time average, if you will, of z plus squared. And this, again, the z plus or minus, those are the Alfvén wave amplitudes. So our wave action conservation equation is this. Steady state. Remember the mass continuity equation, and I can, in that last term, realize the product of rho and u and r hat has zero divergence because mass is conserved now, and I'm in a steady state. So those terms come out of that bracket. And what we find for wave action conservation is this, that there's a quantity that is invariant in radius, and it's shown here in brackets. Let me copy that equation over. What is that quantity? Well, it's a mouthful here. It's the wave action flux per unit mass flux per unit omega times 4 omega integrated over omega. I'm just going to call it the wave action flux. And this is associated with the outward propagating waves. It turns out this holds even beyond the WK limit of small wavelengths, provided the outward propagating waves have a much bigger amplitude than the inward propagating waves, which actually, as a technical point, follows from cross-helicity conservation for those of you who are interested in MHD turbulence. Don't know if David Montgomery is still around, but he was a big expert in that area. So here's that equation. If this were all that were happening, let's solve it for observational profiles of U and VA. This would be the solution for the wave amplitude of outward propagating Alfvén waves. It's very wrong because it gives several thousand kilometers a second fluctuating velocities near Earth. That is completely wrong. And the reason it's wrong is we haven't put in turbulence. But that's what the first part of the evolution tells you. And one thing that's important to get out of this is that if you launch Alfvén waves from the sun, there's no dissipation. Their amplitude doesn't just stay the same. Because the density is dropping, because the flow is changing, it's accelerating, the wave speed is accelerating, the amplitudes actually rise until this point. It turns out that's the point at which it's the so-called Alfvén critical point where U equals VA, and then they start to drop. But you get that rise. How about putting in turbulence? What does that do? Let's put it in now. We had that discussion before about hydroturbulence. The same thing happens for Alfvén wave turbulence. Now, however, there are a couple differences. One is that the size that we care about is the size measured perpendicular to the background field, because that's the direction in which the eddies are moving. I'll call it L perp. That's the eddy size we care about. Also, the turnover time for the Alfvén waves, the Z plus waves, is L perp divided by the velocity of the inward propagating waves, L perp over Z minus RMS, because the outward propagating waves don't interact with each other. Only the counter-propagating waves interact. The turbulent heating rate is an energy density, rho z plus squared, divided by that eddy decay time. So this is our turbulent heating rate. To calculate it, we need a prescription to get this z minus. We need to figure out how to estimate inward propagating wave amplitudes. You can do that quite simply. This goes back to an idea by Alfvén-wave and colleagues in 2002, something Joe Hoyt and I extended to account for solar wind outflow in 2009. The basic idea is you simply balance the rate at which these inward propagating waves are generated by reflection against the rate at which they are dissipated by the turbulence. The rate at which they're generated by reflection is this. This quantity here, the U plus VA times dVA dr over VA. That's just the time rate of change of the Alfvén speed divided by the Alfvén speed in the frame moving with the waves. It's like a fractional time rate of change, a fractional time rate of change in the wave, the Alfvén speed, multiplied by the amplitude of the outward propagating waves. That's the rate at which you generate inward propagating waves. The rate at which you dissipate them is Z plus over L per times Z minus. This is a decay rate for inward propagating waves. I mentioned before, the decay rate for outward propagating waves depends on the inward propagating wave amplitude. Conversely, the decay rate for inward propagating waves depends on the outward propagating wave amplitude, because one direction of wave is sheared by the opposite direction of waves. So in that equation, what's very interesting is both sides are proportional to the amplitude of the outward propagating Alfvén waves, so it cancels. And so we get the following estimate. Z minus over L per, kind of the rate at which the outward propagating wave energy decays, is dependent only upon the Alfvén speed profile and the outward propagating, the solar wind velocity U. This is an estimate. Let's parameterize our ignorance with some constant of order unity here called sigma. And this is, I'll take this as an equation that I'll repeat in another slide or two. How do we build this in to the WKV evolution? How do we go back and, before we had that, this quantity, that wave action flux was independent of R. But now we want to say that it decays with a decay time scale of L perp over Z minus. So how do we write that mathematically? If something is decaying with a decay time scale, what does that mean? It means its time derivative, or the time derivative of its logarithm, is minus 1 over the decay time. And that's what we're writing here, minus 1 over the decay time. This is the time derivative of the log of the action flux. But this time derivative is the one, not a partial time derivative. These are the time derivative moving with the waves. This is a steady state model. There are no all partial time derivatives are 0. This is the time derivative moving with the waves. Why does this matter? Let's put in the previous estimate for that decay rate for the right-hand side. This is based on our simple estimate of the inward propagating wave amplitudes. If you put the second equation into the first, notice they both are proportional to U plus VA. And then we have derivatives of logarithms. And you get this equation, a simple equation you can solve. And that equation, it has a very simple meaning. What it tells you is that every time you move through one Alfvén speed scale, so in other words, every time the log of VA changes by a factor of 2, that the log of this has to change by a factor of 2, roughly. In other words, every time you move through an Alfvén speed scale height, you dissipate a significant fraction of the remaining Alfvén wave action flux. This avoids a fine-tuning problem in the solar wind, actually. Because if we observe the wave amplitudes near the sun and near Earth, there are about 5 e-foldings of the energy. Not 100, not 0.2, but something of order unity. And the reason why that's a fine-tuning problem is that if you were to try to estimate what that was before you knew the answer, you would look to various quantities that you could measure. So for example, what is the correlation length of the waves at the sun? Right? Remember the eddy turnover time is L over delta V. If you wanted to know what's the time scale for these waves to decay, you'd want to know their correlation. So you'd want to know their size near the sun. You might also want to know what's their wave period. What's the wave period of the dominant waves launched from the sun, because the lower frequency waves reflect better. So if you ask how much uncertainty there is experimentally in those two parameters, there's enormous uncertainty. Published studies will vary by 2 orders of magnitude for the dominant perpendicular correlation length of the waves, and by 1 order of magnitude for the time scale. But despite all that uncertainty, we get everywhere that we have about 5 e-foldings of the energy, and this model gets you that automatically. because the Alfvén speed profile is fixed, and it has roughly 5e foldings to it. So if you count going up and down. All right. So you can solve this equation, you can build it into models. I have not too much time left, and I want to save some time for questions. And so let me just tell you what I have here to present, and then justify to you why I'm going to go quickly. The two things that I want to present to you are first, direct numerical simulations that basically validate this hand-waving picture that I've been giving you. They're basically just to say, see, we were right. This is basically, okay. And then the second thing is to say, if we build this idea into one of those models, like Parker and others developed early on, spherical models of the solar wind, tried to accelerate up to 700 kilometers a second, can we solve the problem that they couldn't solve before? And the answer is yes. But really what I wanted to focus on in this talk was more these basic ideas, so I hope you'll forgive me as I really go through very quickly this last part. These are the equations that I was telling you before that describe these waves. My colleague Jean Perez and I have simulated these numerically using large-scale direct numerical simulations. We basically solve those equations within a simulation domain that's a narrow flux tube going from the sun out to about 65 solar radii. The flux tube is parallel to the background magnetic field. We force the velocity at the inner boundary to represent the convective motions near the sun. We include a model chromosphere. We watch these waves go out. We watch them reflect. We watch them interact and decay. And I'll be happy to talk about details either in questions or after the talk. This plot here compares the simulation data this is the curve, the amplitude of the outward propagating Alfvén wave in 4 different runs that are differentiated by the assumed perpendicular correlation length of the Alfvén waves at the photosphere and the assumed correlation time, neither of which we know very well observationally. But for 4 different choices, you can reproduce the simulation with the model that I just presented you. I told you there is that parameter sigma that parameterized my ignorance about this. By varying that parameter from 0.72 down to 0.25, we can reproduce these amplitudes very well. This stuff near the far left, let me explain the axis. R is the distance from the center of the sun. This is the solar radius. So this is basically height above the sun's surface in solar radii. This part is the chromosphere where the model doesn't extend. There you have basically balanced waves going in both directions because waves coming up hitting the transition region between the chromosphere and corona are strongly reflected and go back down. So the punchline of these simulations is, for the purpose of this talk, is simply that those kind of generalized ideas I was presenting really do capture the essence of this type of turbulence, this non-compressive Alfvén wave turbulence. What happens if we add this turbulence to a solar wind model, similar to the Parker model? Some colleagues and I explored this in 2011. We built a model that actually included a fair amount more plasma physics in it than those original models. We closed the model at a higher order in the fluid hierarchy. We closed it at the 4th moment of the distribution function. We allowed for temperature anisotropy, micro instabilities that would regulate temperature anisotropy. We had an analytic model for dividing up the turbulent heating power into protons and electrons, perpendicular and parallel heating, that we based on theories of the dissipation of this type of turbulence. We can run this model compared to a wide range of observations. I won't show all of them. It does fairly well if you compare it to observed temperatures of protons and electrons. Also shown here, for simplicity, is just the fact that the model velocity has no trouble hitting 800 kilometers a second for wave amplitudes at the sun that are constrained by observations, such as the movie I showed you of those oscillating features. This is the density in the model. These are observations of a polar coronal hole, observations from Ulysses for a higher distance. This is one other thing from that model that sort of shows, I think, an important conceptual point about this model. This is a plot of the 5 different contributions to the total energy flux of the solar wind as a function of radius. So Fu is the energy flux in the kinetic energy outflow of the solar wind. Fw is the energy flux in the Alfvén waves. Fg is energy flux for the gravitational potential. It's negative. Q total is the total heat flux. Fe is the enthalpy flux. What you see is near the sun, towards the left, almost all the energy is carried by the Alfvén waves. In fact, they carry more energy than you have out the total out at large distance, because they have to lift the plasma out of the gravitational well of the sun and then offset this negative gravitational energy flux. If you go far from the sun, the Alfvén wave energy is all dissipated, the kinetic energy of the flow is grown, and that's carrying all the energy. So this model is basically one in which you're converting one form of energy carried by waves almost entirely by waves and almost not at all by convection. You're transferring that energy, transforming it into kinetic energy.
Is that the reason the 10 solar radii is just
That's a really good question. 10 solar radii is roughly the Alfvén critical point. And the reason it was chosen is that we would have loved to have gotten in closer, but it was very expensive to get in closer. There was a much more expensive option on the table to go in closer with one flyby. But this mission will have many flybys, and so it was less expensive, longer science operation window. But at least we get roughly to the Alfvén critical point. All right, so I'm going to end with just a list of questions that the Parker Solar Probe will address. One of them will be to resolve whether this type of model that I've been presenting, which is the leading one, it is not by any means my model. It's something that goes back to more than 50 years. Parker in the 60s, Coleman in 1968, but many people have worked on it. We still don't know if it's right. This mission is going to tell us a lot that we've never been able to measure before. Also, another big question in the field right now is how exactly does this turbulence dissipate? And the region near the sun is very different from the region we've been able to access so far in terms of the key plasma parameter, beta, which is the ratio of plasma pressure to magnetic pressure. That dimensionless quantity is small near the sun. It's about 1 near Earth. And so we don't know how that process works in the region where the solar wind is heated and accelerated a little strongly. Also, here's some other more technical consequences. I mentioned technical questions. I mentioned alpha particles being an important constituent of the solar wind. Well, one thing that they do, which is quite interesting, in the fast solar wind, is somewhere close to the sun that we haven't been able to explore yet. They are strongly heated and they form a beam that flows away from the sun faster than the rest of the solar wind. And that beam carries with it free energy, a lot of free energy. So much free energy that just the slowing down of that beam between 0.3 AU and 1 AU is a lot of energy, similar to the amount of energy that you need to heat the protons. But extrapolating in towards the sun, it seems like that becomes even more important. And we don't know where that beam originates. We don't understand that beam at all. This mission will tell us. Another open question, how do Alfvén waves interact with compressive fluctuations? The Alfvén wave is non-compressive. It doesn't perturb the density, it has no divergence in the velocity flow. But we would like to know how the Alfvén waves interact with other types of waves. Also, I mentioned this about the beta decreasing to small values. How does that affect the dissipation of turbulence? Also, how does it affect solar wind turbulence more generally? Another big question is, what is the origin of the slow solar wind? This in many ways is a more complicated question than the fast wind. Because the fast wind, if you recall from that early plot from Ulysses, it's fairly uniform. By comparison, the slow wind has much stronger inhomogeneities. It is emitted from a part of the sun where the magnetic geometry is much more complex. The fast wind comes from more of these open field line coronal holes. The slow wind seems to come from either closed structures or the boundaries between closed magnetic loops and open field regions near the sun, where a lot more physics can come into play. That's another topic that will be greatly illuminated by the Parker Solar Probe. With that, I'll stop. Thank you for your attention.
Thank you. So let's take a couple of general questions, and then I think you'll be here for a little while afterwards.
Yes.
So, Robin?
So the sun is rotating and the magnetic field's not radial. Is the length scale of that, is that important, or is the length scale just longer than the...
For the origin of the solar wind, it is likely not important. And one way you can get at that is that you can ask, there's this other one of the many famous results from Parker is the Parker spiral field, which I'm sure you know of, but for the rest of the audience, where if you imagine the rotating sun with field lines coming out from it, as the sun is rotating and the flow is going radially outward, the field lines end up tracing out this Archimedean spiral. And there's a characteristic radius in which the field lines transition from being basically radial near the sun to more azimuthal, farther from the sun. And the point at which they reach 45 degrees is about 1 AU in the slow wind, and it's even farther in the fast wind. Most of the action on the acceleration of the solar wind is within 10, 20 solar radii. And so there, it isn't a great film. But one of the other things we're hoping to get out of this general topic of study is a better understanding of astrophysical outflows more generally. And those include rapid rotators where rotation is key. And so there will be connections to things we learned from Parker Solar Probe to systems in which rotation plays an important role.
I guess presumably if you get this model right, then you can always add that into the model.
That's the hope.
Building on your last point, I guess, the velocities of the fast solar wind are not so different than when you get from accretion disks around compact objects in black holes or neutron stars. And those also have strong magnetic fields, and the magnetic fields are even driving the accretion itself. I know that this is something people think about. I'm not an expert on it at all, but is it a similar process that it could potentially be driving outflow from?
I am very interested in this question. In fact, one of my colleagues at UNH, Francois Foucard, and another colleague, Sasha Tchaikovskoy, and I, basically did this calculation this year for a general relativistic plasma. It's doing this in GRMHD. And it turns out, which actually amazes us, that this basic approach, the basic result, carries over, regardless of whether the flow is relativistic, whether the relativistically hot flow, even regardless of your metric. You get the same basic result. An appreciable fraction of the Alfvén-wave flux dissipates in each Alfvén speed scale height. So we were interested in, if you imagine an accretion disk where there's MRI-driven turbulence, shaking up the foot points of field lines going up into an overlying outflow, what would happen to the energy flux driven by the disk? And so we have some preliminary estimates of the luminosity in Alfvén waves in that particular system. And I think one thing it could do is help control the mass outflow rate in those systems because these waves dissipate close to the central object. They can heat a corona. You increase the temperature, you increase the density scale height. You load more mass onto the field lines. So we think incorporating this into systems like accretion disk outflows could be very interesting. But we don't have any detailed modeling results yet. But hopefully sometime.
So I get the impression that this model does not really apply to slowing generation.
That is actually hotly debated. There is one school of thought that thinks that the same model works for the slow wind. And the idea is that the reason why the slow wind is slow is that if you think about the field lines coming out of a, say you have the sun. I should have guessed that this would. I'll just wave my hands. Basically, if you imagine you have a helmet stream, a closed loop near the sun, and nearby an open field line that's opening up, the field line has to expand a lot to sort of fill the volume over the nearby closed loop. And that's the typical geometry for open field lines feeding the slow wind. And so when you have that rapid coronal expansion of the flux tube, it slows down the outflow, and it pushes the sonic point, the point at which the flow speed first hits the sound speed, further out. And then inside the sonic point, you're dumping in a lot of energy, but that energy, a lot of it is conducted back to the chromosphere. So what that does is it heats it up, so you get a hotter corona, draws out more mass, but you've lost energy per particle. And so it ends up being a slower flow ad infinitum. So that's one school of thought. Another school of thought says, no, it can't be that. It's got to be something else because we have all these other signatures, like composition differences in the abundance of low first ionization potential elements. And then there's yet another rebuttal. Well, maybe these these open field line models can account for those. But this is very much an active area of research and debate.
Right, thank you.